Hi there, I'm Jorge, and in this video we're going to talk about Go language, and artificial intelligence. Artificial intelligence has become a hot topic in the recent years because we have seen solutions to problems that we used to think that they were unsolvable with computers, or at the very least very hard. And one of these problems could be self-driving cars, in which you have a lot of data coming from different sensors and different cameras, and you want to make sense of it in order to take the decision on what to do next in the car. Neural networks are a good fit for this kind of problems where understanding or interpretation of the data coming from different sensors is required. And the way they work is they have a configuration, a series of layers and parameters that communicate the different layers, and you have some inputs and some outputs. The inputs are whatever comes from sensors, cameras, written text, and the outputs are what you expect to be an interpretation or a decision on the neural network. You use some examples, as in real life for humans, to teach the neural network on what has to be done and train it. That is the training part of the neural network. Once you have adjusted all the parameters of the neural network to provide the outputs expected in the training set, the data that you have used for training the neural network, you use this neural network with the values of the parameters that you obtain in order to do inference, to apply this to new inputs. In this video, we are going to find a project that is relevant to us, that can be solved using artificial intelligence, and we will be writing a server using Go that uses artificial intelligence in order to solve that problem. So, get ready, fasten your seatbelts, and let's code. If you have watched any of my previous videos, you have probably realized how much I look like Leonardo DiCaprio or Brad Pitt. But believe it or not, some people don't take my word for it, and they trust more artificial intelligences than myself on this fact. So I have decided to write an application that takes information from pictures and finds the matching celebrities for that picture. In this case, we will write an application that takes a picture from a web frontend and find 3 matching celebrities. And not only that, it will give us the explanation on why it believes that these celebrities look similar to the picture provided through the frontend. That's it. So let's first talk about the organization of our application. In our case, we're going to separate the front end and the backend server. The front end will take care of capturing the image from the user and sending it to the backend. And then when the backend replies, it will display the images of the celebrities and the explanation of why they look similar. But this is not a conversation about front-end. If you're interested into that, probably you should look for better people to explain you JavaScript or PHP. In this case, we're going to talk about Golang, about the Go language and how to write this backend that will be doing the heavy lifting here. The backend will take the request from the front-end. It will parse the data in order to obtain the image. It will standardize that image, we will mention how later, and pass it on to the first model. This will be an AWS Bedrock model that will extract characteristics of the data in the image. And then it will also do the search for the similar celebrities in the database. And finally, it will ask to another model for the description on why they are similar. That's the Go server that we're going to write, and we will do this step by step, writing the Go code from scratch. Let me talk a little bit about the AI models that we're going to use. As I mentioned before, these neural networks that we're using require some training. And we're going to use two different models that have been trained to behave differently. The first one is going to be Titan, and it takes information from an image and it extracts characteristics from the image. Those characteristics might be the way you smile, the shape of your ears, the shape of your nose, or the color of your hair. But we don't know how they are encoded in the characteristics that we obtain. Instead, what we get is a vector of 1024 characteristics. We can adjust it to be smaller or bigger, but this number will work for us. And all of these numbers, they go from -1 to 1, and we don't exactly know what they represent. What we know is that they are useful to match or differentiate pictures. And this is how we're going to use these characteristics, this vector of 1024 values between -1 and 1. The other AI model is trained in a different way. It is a conversational model. It supports a message API, and it does something similar to the AIs that you are aware of in some other parts of the network, like ChatGPT or any others. So basically what we do is we encode the information and we ask it to continue the conversation. We have a prompt that tells the model, this is what we want, and we get information out of the model. Basically, the model is trying to use some probability to predict what the information is that we are expecting based on the inputs that we have provided it with. The inputs in this case are not going to be just text, but rather we will be using images and text. So this is called a multimodal prompt. And it will be the one that will give us the description on why the images look similar. When we use the first AI model, as I said before, it provides us with a vector of characteristics of the image. But it doesn't tell us how similar or close it is to other images. We have to do that. And we use MongoDB vector search in order to find the closest images to the one that we have provided. And the way we do that is by using an n-dimensional search. So we assume that we have an n-dimensional space, and we are looking for the images that are also located in this n-dimensional space that are closer to the one that we have entered, the one that was provided by the user. Probably this n-dimensional space sounds a little bit weird, and it might be, but think of it in terms of other searches that you do that are not related to the value of a field. For example, if you're looking for people that are 25 years old. That is not what we're doing here. We're doing things that are closer to when you do a search for the restaurants that are nearby or the closest gas station to where you are. In that case, you are looking for these points of interest in a two-dimensional space, basically longitude and latitude, or x and y, or however you want to encode that. The thing is that you are not searching for places that are closer for the first coordinate and then that are closer for the second coordinate, but you are interested in the ones that have the closer, or the smaller rather, distance, Euclidean distance between you and the point of interest. But calculating the Euclidean distance, calculating the length of what it would take you to walk straight from your place to the next place, would be a little bit hard and expensive computationally. So what you do instead is you start clipping this space in order to find an area where then you can narrow down to the number of points that you're interested in. Same thing happens for an n-dimensional space. The only thing here is that it is much harder to imagine how an n-dimensional space, in this case a 1024 dimensions space, is going to be visually. Just assume there is an extrapolation of that, and these 1024 different dimensions are what it is used for each one of the different characteristics. And you're looking for the places, the points of interest, in this case the celebrities, that are closer to the one that you have provided. Obviously, the result of that will depend on how many celebrities you put into that n-dimensional space, and the matches will be better or worse based on that. But this is how vector search works, and it doesn't apply exactly to the actual data that you have in the database, but these are two things that we have to match in order to get better results. So let's now use it from our code and write the server using Go. Before we begin coding, let me summarize the steps that we're going to follow in order to implement this backend using Go. So as I said, in the front end, we will capture the image and we will send it to the backend. So the backend will be running an HTTP server and will obtain the serialized request from the front end. It will extract the image and get rid of the metadata. It will also standardize this as part of the handler, the HTTP handler, that will take care of the whole request. The standardization is where the image is going to be resized to a given size that we have defined. In this case, 800 by 600, because we want all the images to have the same size, because we want to avoid the differences between different webcams. With that image standardized, we're going to use it to pass it to Bedrock, to Titan, to obtain the characteristics vector. This is called the embeddings by the AI bros, and the embeddings is what we're going to use later to do the search. So we're going to call Bedrock, obtain the embeddings. Then with these embeddings in place, with this embedding for the image, we're going to use it in MongoDB with our celebrities database. If you don't have one, you can create it with your family pictures, more the merrier. You find who is closer to your kids, your family-in-law, or yourself. But the thing here is that you have to have enough pictures to make the difference. Once you have this database that will have to contain all the embeddings, also for each of the images that are there, we're going to use MongoDB to use vector search and find among all these embeddings the ones that are closer to the image that we have provided. Then it will reply to us with the 3 images there. We will be using the aggregation pipeline, as you will see later, and we will use the 3 images that have been selected as the closest match to talk to another artificial intelligence model called Claude that will provide us with a description on why the 4 images, the one provided by us and the 3 provided by the database, look similar. We will pack all this information in another structure, serialize it, and send it back to the front end to present it to the user. That's basically what we want to do, and this is the code that we're going to write from now on. But if you want to play with the final solution rather than implement it now to understand how it works a little bit better, you can use the URL that is in the references of this video in order to get there and find if you look closer to George Clooney or to anybody else. So let's go and code. So for our backend, we're going to write an HTTP server with a single HTTP handler. And in this handler, we will be sending the data and the requests to both AWS Bedrock and the MongoDB Atlas cluster. So let's start by creating the module of the Go program that we are going to write. And we're going to do that by opening the terminal and then using Go mode init and the name of something that is only ours. So now that we have created that, we can dismiss the terminal and we can create a file that is going to be here somewhere. We're going to create a file that is going to be called server.go. This is where we're going to put our code, and we don't need anything fancy here. We could have more files and split the code among them, but instead we're going to put all the code in the same file just for the sake of simplicity. So let's start by creating the basic structure for a Go file, for a Go program. And here I'm going to add a new type. The type is going to be called app, and this is where we plan to store the dependencies for our project. So we create a method for this new type, and it is going to be called start. The reason why we get the red underlining there is because we don't have the imported modules, the imported packages, and here by saving I get them added to the project. So now we have created the address for our HTTP server that is going to be listening on the IP of this machine on port 3001, and it will record this in the log. That's basically it, and it will start listening and serve requests, HTTP requests. So now that we have that, we can go to the main function and we can create an instance of the app the type that we have just created, and initialize the server using the method that we have just defined. That should be enough, and we can go and in the terminal, we can go and run the code and see that it does what is expected. Okay, so far so good. Let's start now with the endpoint, with the handler. Now that we have our server up and running, we're going to define a handler. This will be the endpoint that will be used to send the data from the front end, and is going to be implemented using a typical handler, an HTTP handler. So let's get rid of the terminal first here, and we are going to define this handler as a new method of the app type that we created before. This method is going to take an HTTP response writer and an HTTP request, as it is always the case for a Go HTTP handler. We are going to save this, and the HTTP method is going to be added here. And the only thing that we have now to do is to include this handler in the router. So we're going to do this by saying that this is going to be a post method, and this is the path that we want to use, and that it will be invoking the method that we have just defined here. So the reason why we have this /API at the beginning is because we want to be able to separate the front end and the back end, and the /API will help us use something like Nginx at the front of our application, and some requests will be sent to the front end, some others will be sent to the back end, and the path, the /API, will tell Nginx that this is what we want to do for this request, to send it to the back end. So that should build. Let me try to do that, and I'm going to just build, and it works. Okay. With the basic infrastructure in place, we can now proceed to obtain the request and standardize the image that we get from the front end. Let's go step by step. So the first thing that we would like to do is to define the structure that is going to represent the data that we get from the front end. We're going to do so by having this structure defined inside of the scope of the handler. So this is the celebrity match request. This is what is sent by the front end. And it may have other data, but we are only worried about the image 64. This is the only thing that we care about. That is going to be called in the JSON file that we receive image field. Okay, the image attribute is the one that we are looking for. Now that we have that, we want to deserialize the request. And we do that by using the typical decoder from JSON that will read the body, and if there is any error, it will complain. But if everything goes well, because we have set this image request type to be of this type structure, it will put the data of the image in this structure, in this instance of this structure. Now that we have that, we can go and play with the data. So the next thing that we can do is to split the data between the metadata of the image and the rest of the information, which is the actual image encoded in base64. So we know that the metadata, the part that says that this is image data, that it is a JPEG and whatever, is separated by a comma from the rest of the information. So this is what we're doing here. We're trying to split the string contained in the image field, and we are only concerned about the second part of this string. Once we have this second part, what do we do with it? Well, we can go and standardize this information. And let me put this separated because we're going to have this in a different function. So here we're going to have this private function here that we're going to store separately. What we will do in this function is take an image as a string encoded as base64 and inside of this base64 as a JPEG, and we will return the encoded information again, but in a standardized way. What do I mean by that? That we're going to decode it and we're going to resize the image so it is 800 by 600. This is what we want the image to be. We are going to do this inside of this function, and the first thing that we do is, as I said, decode the base64 information that is contained in this image field here. Now that we have the decoded part, what we're going to do is also decode the information from the JPEG. So inside of the base64, there is image information encoded as a JPEG format. And what we're doing is reading this into an in-memory bitmap, or sort of. Now we would like to resize this information. But in order to do that, we need an additional package, and we're going to add it. So we're going to get this into the project. And now that we have it, we can get rid of the terminal and have this piece of code that is basically, let me move this, is basically creating a new image of the size that we want and copying the original one to this one, but in according to the size that we have defined. With this new image, we have to do the opposite. We have to re-encode it as JPEG and encode it again as base64. So what we are going to do here is exactly that. We're going to define the JPEG that we want to send back and encode the image with this quality, and then re-encode the data as base64 and send it back to the requester of this function. So basically, in this function that we have created, we standardize the data by resizing it and return it back to the format that it was being used, which is base64 with JPEG data inside of the bits. And with this function in place, we can go to the handler, this handler that we created, and at the bottom of the handler, after getting the data from the image, we're going to use that and send it to this function that we have just created. So we are getting the second part, as I said, from the image that we got from the front end, and we are standardizing the size of this image. This part here is only for avoiding having errors here. I'm I don't get a complaint from the compiler saying that I haven't used standard image. I will get rid immediately of this after we move into the next step. Well, it seems that we have all the infrastructure in place, and now we would like to do some inference. We would like to talk to the AI model that we are going to use in order to obtain a vector of characteristics of the image that we have received from the request and that we have standardized in the way that we did with the standardized image function. And the first thing that we want to do to be able to have this conversation with AWS Bedrock, which is going to be the way that we will run the inference using AWS, is by having the AWS configuration as part of our app type. So we go here to the app type and we're going to add it here. But before we add this configuration, we need to add the packages that we want to have added to our project. As if you couldn't read it when I type it, they are the AWS SDK version 2 for Go, the configuration, and the Bedrock runtime. These are the tools that we need, and now we can go and add the dependency here in the app type. Now it has added this to the imports, so GitHub.com, AWS SDK Go version 2 AWS, and we should be able to initialize this. We're going to have a private function to do the initialization, so this is going to be it, and basically it's going to receive a context and is going to take the credentials that are going to be stored as regularly. If you ever have used an AWS configuration, they're usually there. This is the name of the account. Feel free to replace it with whatever name it is that you use for your account. And this will be in the .aws credentials. That will be the name for the account there. So now we save this, and it's using the configuration default with the share configuration profile and the region. That's it. That's all we need to get a proper AWS config. We don't want to invoke this manually, but rather we would like to have a constructor to do that. And we're going to create this constructor right here. So it is going to be the one that provides the app type. And as you can see here, it takes the context that we're going to use to create the AWS configuration and returns that in the structure. So now we don't need to do this funny thing that we were doing here manually. But let's go step by step. The other thing that is going to be useful for us is the Bedrock thing. So the Bedrock thing is the client for Bedrock. And once we save, we have added this Bedrock runtime to our modules. And here we have the ability to have invocations to the different models that are provided by Bedrock. So we also need a private function that takes care of this, or rather, in this case, since this is a single line method, we're going to do it here. Okay, so the only thing that is different is that we are not creating the type with one field, but with two, and we return this as the value, actually the reference that will be used here. So basically what we are going to do is create a context and get rid of this initialization that we were doing with the literal. And now we use the constructor with the context, and we have in this instance of the app type, the configuration for AWS and the client for Bedrock. So we are ready. We are ready to talk and to do inference in AWS Bedrock for the picture, the image that we have obtained from the front end. Let's add another private method here after the standardizing one that will take care of that part. So here I'm going to add this new method. It takes a context, it takes the image string that, let me remind you that this is the base64 encoded version of a JPEG image that has been resized to 800 by 600 pixels. And it will return a slice of float 64 numbers and errors. An error if something wrong happens here. So let's go step by step, and let's first define what the name of the model that we want to use is going to be. And in this case, we are going to use Titan. Bedrock offers different models with different purposes. Titan is one that is meant for getting embeddings of images. And by having this string defined here, we can invoke the model that we put in the string that we pass on the request. The other thing that we would like to have is the structure that we are going to use to send the data to this Titan model. And this is in the documentation of the AWS Bedrock. You go to the model that you want to talk to, and you learn what the structure that you want to use is. In this case, the structures are going to be these two. The actual request is going to be here, but the request has different options, in this case just one, which is the length of the embedding. The model can provide different embeddings with different lengths. In this case, we're going to use 1024 for the size of the embedding that we are getting. I think it offers 768 and 2048. 1024 seems like a good size for the embedding, and this is the one that we're going to use. The other things that we need here are the input image, that is the base 64 encoded version of it, and the encoding config, the one that we have defined here with the size, and an input text that, as you can see, because of the omit empty, is optional, and we're not going to send it. So let's define the payload using this data that I have just shared with you. And the payload is going to be an instance of this Bedrock request with the image, with the size, and no text. And what do we do with this payload? Well, the Bedrock request is always using the same type of structure, but in order to be able to talk to different models, it requires that there is a field that is called the body that contains the serialized version of the payload. And the first thing that you need to do in order to get that is to serialize the actual version of the payload. And we do that using the normal way of doing this in Go, which is marshalling. We're getting a string that contains the Bedrock body, and if it fails, it will complain. Now that we have the Bedrock body, we're going to prepare the invoke structure that we're going to use. And we do that by using the one that is defined in the Bedrock runtime. And it contains three things: the name of the model, the body that we have just created, which is a serialized version of the structures that we defined at the beginning, and this content type JSON that is also a text string that we're going to define at the top of our program because we're going to use it somewhere else. So this is a constant, and now we can go back to the bottom of our code and continue here. Now that we have this, we can do an invocation in order to get the inference. The inference is when you have the image, you pass it onto the model, and it answers with a representation of the image where it has extracted characteristics in these 1024, in this case, different numbers. So what we are going to do here is the invocation of that model, the Titan one, using the image that we were provided by the frontend. So we have the embedding response here, which is textual, same way that we submitted like a slice of bytes that acted as the body here. Let me show you that here. We obtained a slice of bytes here. We are also obtaining a slice of bytes that contains the response, but we need to extract that. And in order to extract that, we're going to use a different package that will help us to not creating the structure, but just focusing on the actual bits of the response. So we're going to go to the terminal and load this other package, which is called JSON, and adding it to our project, we can have this used for obtaining the embedding converted into a slice of float 64s. So we go one by one and we obtain the values, and it is converted into this slice and then return back to the caller of this private method that we have defined, that was compute image embedding. Okay, so the only part that is missing is for getting the inference of the image is invoking this in our handler in image search. So here we obtain the request, we remove the metadata from the image, we standardize it, and now we are going to add this call to the embedding. We are getting the embedding by using the method that we have just created, passing the context with the image, and basically obtaining the embedding that, again, I use the underscore here to avoid complaints from the compiler. That should be it. We have now the embedding. Let's try to figure out how to find other images that look similar to this one. The embedding that we have received from Bedrock can be used to find the best matches among the celebrity images that we have stored in the database using this n-dimensional search in the embedding space. Probably you don't have access to the database with the celebrities, but you can create it your own. You can create your own free Atlas cluster instance and then add pictures following the same process that we have done with the image that we got from the front end. So basically you would take the picture, you would encode it as JPEG, you would encode it as base64, and then you would standardize the size to 800 by 600, and then finally you would compute the embedding. And in each document of the database, you're going to store the image, any other data that is relevant to you, like the name of this person, and the embedding. And then we will use MongoDB to do the search in this n-dimensional space. We already have an instance of the database that contains these pictures for this example, and is the one that you have been able to run using the URL that I mentioned at the beginning. In this case, I'm going to copy the configuration for the string that gives us access to the cluster that contains the data. And I'm going to copy it from the initial version of this project. So this is going to be created right here. Basically, it's a MongoDB URI that we use in a .env file. That is something that is very common when you're creating services and you want to have different configurations, ones for production, for development, for testing. This is one of the 12-factor apps recommendations, and keep the configuration as part of the external file as the environment. And here we're going to consume this using another package that is called go.env. This is going to provide us access to the .env file, and we're going to add it also here. We go back to the code, and here we're going to obtain access to this MongoDB URI string that is passed either by the environment or through the .env. We're going to do it right at the beginning of our main function. So here we're going to use the go.env in order to load the .env file, but you can have this defined as the environment because we're using it through the environment configuration. And if you don't have MongoDB URI either through the .env file or through the environment that is used to invoke this program, then you will have a problem. Now we do have, by this point here, we have either went out of the application because we did the log fatal, or we have a proper MongoDB URI defined in the environment. Now we can add to our abstract here the configuration that we need to talk to the database. And this is going to be, oh, sorry, let me do this from the terminal first. So here I'm going to get the MongoDB driver, in this case version 2, and what we want to do here is to add the dependency to the struct, as I was saying before, and this is going to be the MongoDB client. So hopefully by this moment we will have everything we need in order to talk to Mongo and do the vector search. So let's go and add the initialization of this client to the constructor. We create a new function here, a private method, a private function rather, that is going to take care of talking to the database. Here we will be talking to the database with the standard options and with the URI that we have been provided through the environment. And we connect to the database, and if everything goes fine, then we will get the client. Otherwise, we will get an error explaining what the problem was. With that in mind, we can go and change our constructor, because now the constructor needs to have an additional parameter. This additional parameter is the URI that we were not using before, but we do need now. Now, with this new parameter, we can talk to the function that we have just defined, and the structure that we need to return is the one that now contains 3 parameters. So we talk to the new DB client, and we pass the client through the type that we have defined to contain the dependencies. There's one more thing that to keep in mind for the initialization. So we now invoke the constructor to create the instance using the new parameter. So here we add the invocation with the URI for the MongoDB connection. There's one more thing that we have to take into account after constructing the app type with all the dependencies, is that after the last step of the new app constructor, we have a valid client connection that we should close in case something goes wrong or before we end the application. So we're going to define, after all the initialization functions, we're going to define a method that is going to be called close, that takes care of doing the closing, the proper closing of the connection for the client that we have created. And this thing is going to happen once we have defined the instance. So for us, we have obtained the instance here, and if everything went well, we want to use this in a defer call. We want this to happen at any time when we go out of this scope of the main function. So that's it for initializing and closing the database connection to MongoDB. As we have done in the past with every relevant step of our endpoint, we're going to create a new method that will take care of searching for the similar images in the database. So we go to the bottom of our code, and after the function that we use, that we use to compute the image embedding, we create a new one. This one is surprisingly going to be called find similar images, and is taking the context, as in the previous case, the embedding, then this vector with 1024 floating point numbers, and it will return the array of strings, which will be a slice of base64 encoded images for the images that are similar to the ones that this one represents, this embedding represents, or an error if something goes wrong. So what we are going to do here is inside of this method, we're going to get access to the collection of images. So basically, in an Atlas cluster, you can have several databases, and here we're using the Celebrity Matcher database. And within each database, you can have one or more collections, which are the document model analogous of tables for the relational world. And now that we have access to that, we're going to use one of the nicest features of MongoDB, that you can take advantage of the database server to iterate through different stages in the search, providing different steps that narrow down the search of whatever you're looking for. This is called the aggregation pipeline, and we're going to define each of the stages for this search. In this case, there are going to be only two. And the first one is the vector search stage. So the vector search stage is basically where we're going to do this search in the n-dimensional space that will be finding the closest matches for the embedding that we have provided. Notice that a BSON-D is the structure that represents a BSON document, similar to JSON, but it is serialized format. That is the one that MongoDB uses for storage, which is optimized for storage. And what it does is it has like the name of the attribute of this field and the value. In this case, the value is another document that contains the parameters for this vector search. The dollar, whatever is the stage that we want to use, what type of stage this is. And this is the data that represents how we want to use the vector search. So we want to use this index, that is the one that has been created to search through the different images. The path, the attribute that we want to use for where the embeddings are stored, is actually embedding. And the query vector is the value that we have received through the invocation to this method. We want to have this number of candidates, but we want the 3 best results. That's it. That's the vector search that we are doing. After that, we are going to do the second stage for our aggregation pipeline. And this is the project stage. We're projecting because we may have more attributes in a document, but we only care about the ones that we put here. So we say, we want you to project the data, and the only attribute that we care about is the image. And the number 1 means we want this attribute there, okay? So that's it. These are the 2 stages, and what we're going to do now is to create the aggregation pipeline. So using one after the other, first we will do the vector search, and then we will project the data. The reason why we have this complaining here, the red thing, is because we are not putting the names of the fields for the bson.e, the elements of the bson-d document. You shouldn't care about that. It's perfectly fine. Now that we have the pipeline, we can use it with the image collection, the one that we obtained here at the beginning. So we are going to use the aggregation pipeline with the aggregate method, and we will obtain a cursor. The cursor will give us access to each of the results. In this case, let me remind you that there are only 3 that we will be obtaining, and this cursor is going to let us iterate through the different values of the results. So in this case, as I said, it's just 3, and we want to obtain these similar images and put them here in this structure that we want to use, that contains the ID. This is, even if it's not mentioned here in the projection, the ID has to be ignored explicitly. If you don't ignore it, it will show up in the results, and the image, that is the field that we wanted to be projected here. Okay, so now that we have obtained the images, let me remind you, 3, we want to return them in the standard way to the color of this function. So we have this array of images that we are obtaining here. And let me try to, yeah, here we go. So we are going to have this as a slice of strings, which is actually the array of images. And we are going to generate the standardized version of the image one by one, appending them to the images slice and returning them to the color of this private method. Where do we call this method? Well, at the end of our handler, that, as you can remember, was what we have been doing so far in the image search endpoint. We have been doing step by step the things that we mentioned we had to do. So now with embedding here, we are going to create the invocation to find similar images, and we have the images here. Again, the underscore is to avoid getting the error while we do the next step. Getting the images that look similar to the one provided by the front-end application should be interesting enough. But hey, we're talking about AI here, so we want to do something more creative, more generative. And we would like to talk to the system and let it explain itself why it has decided that these are the right images. Actually, we're going to cheat on that, and I will explain how later. But what we're going to do is we're going to do inference with a different model. And in order to do that, we also go to the bottom of our code, and here we're going to create another private method. This is going to be called getImageSimilarities_description. So it will explain why they are similar, the images that have been provided by the previous method and the one provided by the front-end application. We are going to receive a string with the image that base64 encoded, the one received from the front-end application and standardized, and the 3 images that we have obtained from the database. Also, we are going to return a string that will be the explanation or an error. So let's go step by step, and the first thing that we should do here is, as we did in the previous usage of Bedrock, is to define the name of the model of Bedrock that we want to use. This model, in this case, is Claude, and Claude has a totally different purpose to the one that Titan had. So instead of getting the embedding for the image, this is a model that is trained to work in a message API. So basically you talk to it and you get responses, textual responses. But it can go a step further. I mean, like, one of the advantages of Claude is that it is multimodal. So it is not limiting itself to text. It can also process images, and we can pass the images and ask it, why do you think these images are similar? Notice that this explanation doesn't have to be exactly or at all what the search or in the n-dimensional space, the vector search that we did, has found as similar, but this is a textual explanation of why these images might look similar. So what we're going to do here is first define the structs that we're going to use. And here is a little bit more complex than in the previous case, because we're dealing here with messages, and well, take a look at it, but basically you will see it a little bit better when we define the data. This is defined in the documentation of Claude. And what we are going to do is we're going to put here the data that we want to send to the model to infer the new message, the explanation of why the images are similar enough. So let me go through the payload. As I said, the Claude body is the main structure. This is the version that we're using, the number of tokens that we want to use. This is the system, the prompt that is telling Claude what we want it to do. And then as user, we're passing data that is the different images. Like you can see one for each of the images. It contains the media type, the base64 encoded image, and the type is base64, and it passes that onto Claude, but it also passes this text that contains the prompt. And the prompt has previously been defined here. Please let the user know how the first image is similar to the other three and which one is the most similar. Okay, so this is the prompt that we have provided, and this is what Claude will answer. Now that we have this payload, we have to follow the same process that we did before, like serializing it, put it into the body, and sending it to Bedrock. So let's go and do that. First, we serialize it. We put it into the body, and we use the name of the model here and the content type and what the data that we accept as response. That's it. That's all we need to do the invocation of the model in order to do the inference. And this Bedrock response is what we have to process. And we're going to process it using JSON as we did in the previous case. So basically, after getting this description, we're getting from this part of the JSON message the description on why the images look similar. With this description, we return it back to the caller, and the call has to happen in the search method. Let me find it. A standardized image here. So here is where we are going to invoke the private method that we have just created. And this description is exactly what we were looking for as part of our answer to the user. We just have here to define the structure that we want to use for returning the information to the front end, which is this one that contains a field for the description that is called description, and a field for the slice of images that is called images. And here I'm going to the description is description, and images are images. And hopefully that should be it. Our response will contain the description and the images. And the only thing that we have to do is to use that as the response of our HTTP request. So basically we set the content type to application JSON, or rather, I think that we had this defined here, so we can do this properly. Content type JSON, so we are going to use this here, content type JSON, and here we say that everything went well, and we encode the response that we have created and return it to the caller of this HTTP endpoint. Let's review what we have created. So let's go to the beginning of the code. We have created an app type that in its constructor initializes the dependencies for the MongoDB client, for the AWS configuration, that it is not reused, but it will be helpful if you want to extend the application, and for the Bedrock client. We do this in the constructor, the new app function here, and we close the connection with the MongoDB client in the close method. The start method is the one that organizes the HTTP code, so it assigns this handler to this verb and this path here. And this is the method that takes care of the endpoint. Basically, we're getting the information using this structure and serializing the JSON that we have received from the front end. Then we are manipulating the data, the image that contains some metadata at the beginning, separated by a comma, and using just the part without the metadata, we standardize the image. So basically we decode the image from base64 and we decode the JPEG into an in-memory image We resize it to 800 by 600, and we re-encode it to JPEG with this Q85, this quality factor, so the image keeps most of its content intact. And we re-encode it back to base64. Once we have standardized the image, we send it to compute the embedding to Titan, and this method returns an embedding, a vector with 1024 characteristics that have been extracted from the image that represent the image somehow, and that are used in order to find the similar images in the database, doing this vector search and finding in this n-dimensional space the closest images to the one that we have sent. Keep in mind that how close the images are, the ones that are returned, how similar they are, depends a lot on the number of images that you have, that they have plenty of characteristics, that they are representing every possible image that you have in the real world. With the images that you got back from the database, you can query the other model, Claude in this case, in order to get an explanation of how they look similar. And with these two things, the images and the description, with this messaging API and this multimodal query, we get both the description and the images in a single structure that we serialize and send back to the caller. And that's it. That's all we have to do in order to solve this thing with Go in the backend. In this video, we have written from scratch a backend using Go that uses an AI model, actually two, and MongoDB vector search. We have fully implemented the application that finds celebrities that match what the user looks like, and I have finally been able to prove to all of you how close I look to Brad Pitt. So I will call this a video, and if you finally decide to play with this code and try it and implement it by yourself, feel free to drop a message in the MongoDB community forums and let us know how it went. Meanwhile, stay curious, hack your code. See you next time.